Okay, so in the previous video, we introduced the idea of a recurrence relation as a way of describing a sequence of numbers. And now what we want to start to do is apply those concepts to financial maths applications. So what we want to focus specifically on today are problems that involve linear growth and decay. Okay, and so they are sequences that look like this. Obviously, you've also got the V0. So yeah, sorry, I shouldn't have called that a recurrence relation without the V0 as well. Okay, so we would have both bits, V0 equals something, and Vn plus 1 is Vn plus or minus a value. Okay, so this will change from recurrence relation to recurrence relation, but the key idea is here is what we're looking at is sequences where all we do from one term to the next is to add on a value or subtract a value. So obviously if we're adding on a number each time, an example would be something like this. Initial value is 2, add 3 each time. We get what we call linear growth. And that's because if we were to plot these terms out, we're counting up by 3 each time. Each term goes up by the same amount. Each term goes up by 3. So every time we move across to the next term, we're increasing by 3. Okay? And so they form this nice linear pattern if we were to join them with a line. So this kind of growth is called linear growth. Obviously we would get decay rather than growth if what we were doing was subtracting every time. So if every time we move on one term we're subtracting 4, we're going to get, same idea, because we're subtracting the same amount every time, it's going down by the same amount every time. So it's linear but it's going down, so linear decay. So the sequence modelled here is if the initial value was 20, so that's this marker up here, and then each time we're subtracting 4. So this would be 16, this would be 12, this would be 8, etc. Okay. Alright, so we're looking at those particular cases, linear growth and linear decay. And as I said, that's because if we were to plot them, they form a linear pattern. Okay, so the first financial application that's going to involve linear growth is going to be simple interest loans and investments. Okay, so in all loans and investments, so this is just a general comment about, we'll talk a lot about loans and investments throughout this entire module. In all loans and investments, one party is borrowing money and the other party is lending money. And the entity borrowing the money is the one who pays the interest, and the entity lending the money is the one who earns the interest. So if it's a loan, for example, the borrower is the individual. I am borrowing the money from the bank. The lender is the bank. Okay, so I as the individual, for the privilege of being able to borrow this money that isn't mine, I pay interest to the bank. So the bank earns the interest, I pay the interest. If, however, it's an investment, those roles are reversed. If it's an investment, the bank is essentially borrowing my money. I am giving the bank my money for them to look after it, and as a thank you for that, if you like, the bank pays me interest. Okay, so I earn interest if it's an investment. I pay interest if it's a loan. The bank earns interest if it's a loan, and they pay interest if it's an investment. Okay, so it's really it's really important that you've got those ideas, those basic ideas around loans and investments straight for this entire topic. Okay. The amount of money being borrowed or invested is usually called the principal amount, and interest is like a fee for borrowing money that doesn't belong to you. So interest can be calculated in different ways, and what we're going to focus on here in this section is simple interest. Simple interest is not practically very common. Most loans and investments, compound interest would be what is being calculated, and we will move on to that in this topic. As I said, so simple interest provides an example of linear growth and decay. Simple interest means that the same amount is added to the loan or investment at each time interval. So whether that's every week, day, month, year, whatever it might be, but it's the same amount, a fixed flat amount. So the amount of interest added each time is usually a percentage of the principal amount. So for example, if we have an investment of $100 at 10% per annum simple interest, so per annum is per year, okay, so the time period we're dealing in here is in years. Every year the simple interest is added to the account. So this means that every year 10% of the principal amount is added to the investment. So when it's simple interest, it's always the percentage of the principal amount, which is why it doesn't change. Okay, so 10% of $100 is $10. So what this means is that every year $10 is added to the account. Okay, so after 0 years, that is at the beginning, the amount in the account is $100. After 1 year, it's $110. After 2 years, it's $120, etc. So $10 being added in each time. So we can describe, what we've done here is we've generated a sequence of numbers that we could describe using a recurrence relation. So if Vn is the value of the investment after n years, then we know that V0, the value of the investment after 0 years, is 100. Okay? And we know that we can describe Vn, we can either write it as Vn plus 1 is equal to Vn plus 10, or it would be also correct to write Vn equals Vn minus 1 plus 10. Okay. We tend to go with the top one, but both are correct. So if Vn is the value of the investment after n years, then V0 is 100, the value is 100 after 0 years, and then we take Vn and we add 10 to it to get Vn plus 1. So to get from one term to the next in the sequence, we're adding on $10. And that $10, in this case, was 10% of $100, okay, because we had a simple interest rate of 10% and a principal amount of $100. So a recurrence model for simple interest is essentially going to be a sequence where we're adding something each time. So if Vn is the value of the loan or investment after n years, or n doesn't have to be years, n time periods, then let R be the percentage interest rate. Okay. So for example, if the interest rate is 4.8% per annum, then R should be 4.8. Okay, so don't change it to a decimal. I'll talk more about that. And then the recurrence relation for the value of the loan or investment is this. So V0 is your principal amount. Okay, and then to get from Vn to Vn plus 1, we're adding on D, where D is the percentage of the principal. Okay, so in this case, that would be, if we had 4.8, as we said, if it's 4.8%, that means it's 4.8 over 100 times your principal amount. Okay, if you want, you can think that through straight away in your head as being 0.048, and we want to get good at that. We've talked about that in other situations. So 4.8% is 0.048. So we're doing that multiplied by V0. Okay, but if R is the interest rate of 4.8, the formula needs to specify that we're dividing that by 100. But you can go straight to calculating 0.048 times your initial value, your principal amount. Okay, let's have a look at an example, a couple of examples. $2,200 is invested in a simple interest account with an interest rate of 4.7% per annum. Set up a recurrence relation to describe the value of the investment after n years. Okay, so the first thing we actually need to know is what's the simple interest? How much interest gets added on each year? So that's our value of D if we think about the formula, but again, don't get too bogged down in formulas here. So it's 4.7%, so that's 4.7 over 100 multiplied by 2,200. As I said, if you can make that step yourself to 0.047 straight away, just do it. Okay, so 0.047 times 2,200 is $103.40. So every year we're adding on $103.40, which is 4.7% of the original investment, $2,200. So now we can set up our recurrence relation. So it doesn't tell us what letter to call it. I'm just going to go with V. So V0, the value of the recurrence relation at the beginning, the value of the investment at the beginning is $2,200. Vn plus 1 is going to be equal to Vn. So each term, one term is going to be equal to the previous term plus $103.40. Okay, so the nth year, add on $103.40 and we get to the value in the n plus 1th year, the next year. Use the recurrence relation to find the value of the investment after 5 years. Okay, so after 5 years is V5. So sometimes you need to be a bit careful about that, because V0 is at the beginning. After 1 year would be V1. After 2 years would be V2. So be clear that this means that we want V5. All right, so let's work that out. Let's set up our recurrence relation in our CAS. So 2,200 is our initial value. Press enter. And then we want to add 103.4. Okay, so that's after 1 year, after 2 years, 3 years, 4 years, 5 years. Just be careful that you don't lose control of you pressing enter too fast, that you miscount So after 5 years, the value of the investment is $2,717. Now, I should say that in the financial maths module, now that's not particularly necessary here because it's an exact answer. In the financial maths module, there's a standard instruction at the start that says you should give all money answers correct to the nearest cent. Okay, so that means to 2 decimal places. So try and get in that habit. As I said, in this case, this is exact, so it wouldn't make any difference if we didn't write that. But if this had been rounded, and even if it rounded to 0.00, then I would still need to write 0.00 to indicate there's actually more going on out here. Okay, but to 2 decimal places, that's what it is. Okay. In this case, as I said, it's not rounded to that, it's exactly that, so we'd be okay to write 2717. Okay, determine how many years it will take for the value of the investment to exceed, so be more than, $3,000. Okay, so I'm just going to continue my recurrence until it gets to be more than 3,000. So we're now currently at V5 after 5 years. So let's keep going. This is 6 years. Oh, sorry, just get that out of the way. 7 years, not quite. 8 years. Okay, so V8 is 3027.20. Now, I'm actually going to let me just check. I'm going to press enter and copy this down to my next line just to check that that's exact. One thing I would say to you, when we're dealing with financial maths, we're often dealing with very big numbers. I would strongly advise you, so I've just clicked on the battery at the top there, document settings, to make sure that your float settings are set reasonably high. So which one do I want? No, not calculation mode. Sorry. The top one, sorry, display digits. So the default for the CAS is float 6. I would strongly suggest when you're doing financial maths, at least make it float 8, maybe even make it float 10, because down the track we're often going to be dealing with problems that involve, home loans, and you've got hundreds of thousands of dollars, and if you still need to give the answer to the nearest cent, you're going to need quite a lot of digits displaying. Now, it's possible to override it if you haven't got your CAS settings such that you can see enough digits, and I'll talk about how to do that down the track, but I would strongly encourage you to make sure that you've got your float settings quite high. So V8 is $3,027.20. Make sure that you answer the question to determine how many years it will take for the value of the investment to exceed 3,000. It's not sufficient just to write this down. You've got to answer the question, and so therefore it will take 8 years. So 8 years for the value to first exceed $3,000. Okay, example 2. The following recurrence relation can be used to model the value of a simple interest loan after n years. Okay, so we've been given the recurrence relation. So again, understanding this. So this is our initial value, so we're starting with $12,000, and to get from 1 year to the next, so it's in years, so get from 1 year from the next, we're adding $816 on every year. Okay, so state the principal value of the loan. That's that. Okay, so the principal value is $12,000. Sorry. State the dollar amount of interest paid per annum. Every year, the interest paid is $816. Calculate the annual interest rate of the loan. So we have to work out what is 816 as a percentage of $12,000. Okay, so the $816 out of $12,000, multiplying by 100% to change it to a percentage rather than a decimal, 816 divided by 12,000, 12,000 multiplied by 100. Control enter. So that is 6.8%. So remember, control enter to get your answers as decimals if you've got your CAS set to auto mode, which I usually advise. Although in further maths there's possibly a case for working with approximate, but I wouldn't recommend it. Part D, if the loan is to be paid off in full at the end of 5 years, how much will need to be paid? Okay, so the loan, we borrowed $12,000, it's accumulating $816 every year. We want to know at the end of 5 years, so that's V5, what's the loan worth? So again, let's set up our recurrence relation in our CAS. So $12,000 is our principal, press enter, and then add 816. So that's after 1 year, 2, 3, 4, 5, I want 5, that's it. So $16,080 is the value of the investment after 5 years. So if it's to be paid off in full, this means that 16,080 will need to be paid. After how many years will the value of the loan first exceed $20,000? So we've seen after 5 years it's worth more than $16,000. So let's just continue the recurrence with our CAS. So this is 5. So 6 years, 7 years, 8 years. Sorry, just get that out of the way. 9 years, not quite. 10 years. Okay, so V10 is 20,160, and so therefore after 10 years is the first time that the value of the loan will exceed $20,000. So obviously simple interest is not particularly real world. You're adding on a flat rate every year is not very common. To only do it every year is not very common. And also to have a loan where you just let it accumulate interest without actually making any repayments to pay off the loan is also not very common. So we'll certainly get to more real world applications with compound interest and making repayments, etc., as we move through the topic. That isn't to say that you don't need to have an understanding of simple interest though. Okay, the next part we want to talk about is when we depreciate. So depreciation is when the value of something goes down just over time, just by virtue of the fact that it gets old. So things like cars are really common examples of things that depreciate. So for example, a car purchased for $40,000 3 years ago is not worth $40,000 today, and we say that the value of the car has depreciated. We might wish to use depreciation to calculate the current value of something, whether that's for the purposes of trying to sell it, or whether it's for tax purposes, or we might also wish to decide whether it's time to replace or to write off an item. So often, particularly if you insure a car, there'll be a value at which your car is written off. So if your car at that point is deemed to be worth less than, $5,000 or something, it's not worth the cost of repair, and it's written off at that point. So there are 2 ways for us to think about depreciation. Well, actually there are 3 ways, but in terms of flat rate depreciation, there's 2 ways for us to think about it. One is based on the age of the item. So depreciation might be calculated on an annual basis, and the other would be based on the amount of use that the item has had. So in this case, the depreciation might be calculated based on the number of kilometres the car has travelled rather than the number of years that you've owned the car. And we call that unit cost depreciation. So flat rate depreciation would be part 1, and part 2, example 2 would be unit cost depreciation. Both are examples of flat rate. Okay, it's going down by a flat amount every time, whether that's every kilometre or every year. We'll talk more about essentially, the compounding version of depreciation in another video. So the recurrence model for flat rate depreciation, if Vn is the value of the asset after n years or after n units of use, so whether that's n kilometres or whatever it might be, R is the percentage depreciation rate. So if the depreciation rate is 10.9%, then R is 10.9. The recurrence relation for the value of the loan or investment after n years or n uses is. So V0 is the initial value of the asset, and then we are depreciating, so it's going down, so we're subtracting an amount every year or every time, every kilometre or every time the item is used. And D is calculated as a percentage of the initial value. So as I said, if it's 10.9% flat rate depreciation, we calculate 10.9 over 100 times the initial value, or 0.109 times V0. Okay. And that gives you the amount that you're going to depreciate by each year or month or whatever the depreciation period is, and then that's the amount that we're going to subtract each time. Okay, let's work through some examples. The value of a computer depreciates so that its value after n years is given by the following recurrence relation. So V0, its value after 0 years, that's when we purchase it, was $19.50, so $1,950. And then to get from each year to the next, so n is being measured in years, so each year to the next we're subtracting $350. So state the purchase price of the computer, that's V0. That's the initial value of the item, so $1,950. By what dollar amount does the value of the computer decrease every year? The recurrence relation tells me it goes down by $351 every year. calculate the rate at which the value of the computer is depreciating. So again, that's about us working out what is this as a percentage of the initial value, the purchase value. So we want 351 out of 1950 multiplied by 100% to convert it to a percentage. So 351 out of 1950, 50 times 100, Control Enter. So that is 18%. So it's 18% depreciation per annum. Use the recurrence relation to find the value of the computer after 3 years. Okay, so again, let's set up the recurrence with our CAS. So we type in the initial value first and press enter, 1950, and then we type subtract, which will mean we subtract from the previous answer, 351. So that's going to be after 1 year, 2 years, 3 years. Okay, so the value after 3 years is only $897. The computer will be replaced once its value falls below $500. After how many years will this occur? So let's keep recurring. So this is after 4 years, not quite, after 5 years. So V5 is 195, so therefore will be after 5 years. That's the first time the value goes below $500, even though it ends up quite a long way below $500. Okay, example 4, sorry. Some days the keyboard just won't go away. A bicycle depreciates at a rate of 50 cents for every 100 kilometres it travels. The bicycle was purchased for $300. Set up a recurrence relation to describe the value of the bicycle, after it has travelled in lots of 100 kilometres. Okay, so initial value of the bicycle is $300. The value of the bicycle after n plus 1 years is equal to, n plus 1 lots of 100 kilometres is equal to the value of the bicycle after n lots of 100 kilometres minus, now we subtract 50 cents each time, which is, we can't change the units, this is in dollars, okay, everything's in dollars, so we have to write this as $0.5. We're subtracting 50 cents every 100 kilometres. Use the recurrence relation to find the value of the bicycle after it has travelled 1,000 kilometres. So 1,000 kilometres is 10 lots of 100 kilometres. So this means when n equals 10. So we want to find V10. Okay. So we're going to have $300, press enter. We're subtracting 0.5 each 100 kilometres. So that is that's after 100 kilometres, after 200 kilometres, 300, 400, 500, 600, 700, 800, 900, 1,000 kilometres. So that was V10, and it is $295. Part C, how long will it take for the bicycle to be worth nothing? Now, we're going to be recurring a long time here, okay, because it's only going down by 50 cents every time. And it shouldn't really say how long. It will be after how many kilometres. How many kilometres? Okay, so what we actually want to think about is how many lots of 50 cents is there in $300. So in this case, if we were just to keep recurring, we would be here a very long time. Okay, so $300 divided by 50 cents. How many lots of 50 cents are there in $300? There's 600 lots of 50 cents. Okay, so this means it's going to be 600 times 100 kilometres is going to be the distance that we'd need to travel. So that means that we're going to have done 60,000 kilometres on our bike in order for it to be worth zero. Now obviously a bike doesn't depreciate significantly. It's not got a motor, and it's not got, electronics, etc. So it's taking quite a long time for the bike to be worth nothing, and it only goes down by a very small amount for every 100 kilometres of use. So it's going to take 60,000 kilometres in order for it to be worth nothing. And that's because 60,000 kilometres is 600 lots of 100 kilometres, and 600 times 0.5, which is how much we depreciate by, is 300. That's equivalent to the purchase price. So it would have lost $300 worth of value and now be not worth anything. Okay, so the work for this section was from exercise 8C. looking at linear growth, so simple interest investments or loans, and linear decay, so flat rate depreciation or unit cost depreciation.